Where do photons come from? I'm curious why we say the universe exploded in the Big Bang, why black holes can't just be dark matter, why when a star goes supernova, space still bent for a black hole, gravitational waves, the fabric of space. Did you get all of that?
Wow. Whoa. That's somebody that had Red Bull that morning.
Yes.
This is StarTalk. Neil deGrasse Tyson here, your personal astrophysicist. We're doing cosmic queries today. Grab bag. Ooh, yeah. And I look to my left. I don't see Chuck Nice. Hey, Chuck, what did you do?
We look a little different.
Harrison Greenbaum, welcome back to StarTalk.
Yes, it's so nice to be here. Thank you for having me.
Yeah, last time it was BC, before COVID.
That's right.
When you last
That's
made an appearance
We
here.
had a whole pandemic in between.
A whole pandemic in between. And also you had a Las Vegas residency in there.
Yeah, I went across the country and back in that time.
And back. So just congratulations on where your talents have taken you.
Thank you.
And now you're right here in my office at the American Museum of Natural History.
As much going on here as the circus, I will say.
No, well, the universe is a circus unto itself.
Absolutely.
And it's many more than 3 rings going on there. Yes. Saturn's got rings. Multiple ring circus in the cosmos. So this is a grab bag. And you got the questions. I haven't seen them. And because it's a grab bag without an expert that we bring in. So I'm your expert.
Fantastic.
I'll do my best. If I don't know an answer, I'll just say, I don't know. Okay.
Okay.
But you have to.
We have Siri. We have tools at our
We have ChatGPT. You've got
Yeah.
the ways to bail me out is what you're saying. Okay. All right.
If we don't know, it might be known.
Okay. All right. So what do you have first?
All right. So we have Lena McGrath. She writes, "Hello, Neil. I'm Lena from Orlando. Where do photons come from? For instance, are they already inside my birthday candles or are they created from the fire?"
Oh, I love that.
Does not specify what birthday she is on.
Does not. Okay.
Does not.
But the fact that she still uses candles.
Yeah. Right?
What age would you say you stopped using candles?
Once the cake is too full.
Yeah, I think I stopped at 30.
Oh wow, that's longer than I lasted.
I made it high in there.
I think after high school I was candle free.
So it's a great question. It's reminiscent of a famous essay from the 19th century written by Michael Faraday, and it's called "What is Fire?"
Ooh.
Because what is it?
It's an emoji I use too often.
Oh, okay. I've seen the emoji. Can you touch it? Can you grab it? Can you hold it? Not really. So what is it? So that's a famous essay from the 19th century. So a photon is a packet of energy, of pure energy, and it moves at the speed of light. It's the only thing it knows how to do is move at the speed of light. And so by the way, energy can manifest in many different ways, okay? You can have potential energy. Why is it that you can harm yourself by jumping out of a window, okay? There's a reason for it.
Okay.
Because when you hit the ground, energy killed you.
I thought it was the sidewalk.
Okay, you had energy in your body.
Yeah.
While you were falling.
One Red Bull right before the show.
Right, and yes. And the energy kept accumulating as you fell faster and faster.
Right.
Then you hit the sidewalk. All the energy that was in you from your motion, kinetic energy, goes back into you as mechanical energy. And the only way your body can accommodate mechanical energy is to break stuff, because it takes energy to break your bones.
Sure.
Energy can manifest in different ways. And the higher you take the elevator before you jump out the window, the more energy you have to break your bones upon hitting the sidewalk. That's why jumps from higher altitudes will do more damage than from lower altitudes.
But if you're watching this and thinking about it, don't do it.
Do not try this at home.
Don't do it.
Now, above a certain height, there's an air resistance. You hit what's called a terminal velocity, where the air is absorbing away some of that energy.
I am about to terminate. Be terminated.
Terminal velocity to be terminated. So there are other ways that energy can be stored, like inside of an atom. And an electron can sit in many different energy levels. The atom has energy levels within it. It's not a continuous placement of energies. If there's an electron at a higher energy level and something happens to make it drop to a lower energy level, it just lost energy. Where did it go? Actually, it can go in one of two places. If another atom hits it, some of the energy of that electron can go to the kinetic energy of the other atom as it careens off. Oh, this happens a lot. So it's a kinetic energy. A flyby looting of its energy.
Right.
All right. So, but occasionally it just sort of jostles it. The electron de-excites, goes to a lower energy level. Where does that energy go? Bada bing. A photon is released from the atom of exactly the same energy as the difference between the energy levels of the electron. All the energy is accounted for. And so, and the photon goes in a random direction at the speed of light. That's where photons come from. They come from ways that used to be energy in an atom or the vibrations of atoms and molecules and other particles. And in those vibrations, it can lose energy by releasing a photon. And that's what's going on. And it happens all kinds of ways. If you have an electric stove and you turn it on and eventually it glows.
It goes like blue, orange, goes to different colors.
I hope your stove doesn't glow blue. Glow.
You can tell, by the way, how much I cook by my inability to answer this question.
You have no idea
I'm like,
what
I
a
think
stove
blue?
is. You have no idea what, you were right astrophysically, but in the kitchen, you're completely wrong.
Okay.
So the hottest your stove is going to get is red hot.
Gotcha.
But if you had an infinite knob, it would glow white hot and eventually blue hot.
That's gonna be my band name. If I ever form a
Blue
band,
Hot?
Infinite Knob.
Oh, infinite knob.
Blue Hot's better.
But one of those, pick one. I'm
Yeah.
good with you. I'll come see you.
Okay, great.
So the fact that the stove is glowing red is emitting light, red light. So you have vibrating particles in the heating element of the stove, and those vibrations will actually release light. And that, in a way, is cooling the stove, except you keep pumping energy into the stove.
Right.
If you turn off the stove, it's still glowing red, but then it sort of fades away. Why? Because it's giving up all its energy without it being replaced. And if it's hot but not glowing red, it's still giving off photons, but not red photons. If it's hot, what is that? Do you remember?
Don't touch it.
No, still don't touch it until it's cool. So it would actually, if you put on infrared goggles, it would be glowing in the infrared. That's still a form of light. You can have infrared photons. So all these ways will generate photons, and stars are doing it every moment of their lives, and photons are crisscrossing through the universe, and it'll continue that way until the last star dies.
So what does that have to do with birthday candles? No.
Oh, good, very good. Okay, thank you for bringing it back on point.
I feel like Lena is at home right now. She's celebrating her birthday. The candles already melted down. It's ruined the cake.
It's like, Neil, where's the answer? So you have to give energy to the candle from somewhere else, a lighter or a match, right? There's no free lunch here, right? The energy's got to come. So what that will do.
Free cake.
Okay, free cake. You will light the
wick.
You will light the wick of the candle, which is typically coated in wax, because the candles are made of wax. So you ignite the wick that will use molten wax as a fuel source. There you have it. Now, why doesn't the whole candle burn up in one instant? Because the wick is drawing the molten wax in, and if you have too much of the wax, it'll put out the flame. You need just the right amount to feed it and keep it going. And candles are beautiful this way, okay? If the candle gets sort of, have you tried this? Who has candles anymore? But you have like a 3-inch candle, let's say, and it's got liquid there. If you sort of tip liquid towards the wick, you can extinguish the wick.
Right.
You say, well, why is that if it's using the wick to light? Have you ever questioned this?
I have a couple of scented candles. Most of them smell like my apartment burning down when I fall asleep.
Why does the liquid wax put out the wick when the wick needs the liquid wax to burn?
Right.
Because it's too much at a given time. It's too much. So the wick draws it at just the right amount that it could burn the little bitty drops that come in at the rate that you need. So the energy, the starter energy, comes from the match or from a lighter, and you hit the wick. Now the wick simply burns the wax. And wax is one of the great things that kept us lit for centuries, wax candles, the 17th, 18th centuries, we didn't have light bulbs. So candles was a thing, wax candles. So wax is a fuel source. By the way, if you get wax hot enough where it goes molten and you just keep heating it, it can burn without a wick.
What?
So this happened to me at home. I ignited the entire surface of the liquid wax in the pot. And
I thought you told the police it was an accident.
No, I used to make candles, okay?
I'm just trying to picture this birthday party.
Okay, no, I used to make candles. So you melt the candles and you can dip. What happens is you dip a wick in so it gets wet with wet wax. You put it in the air, room temperature air will cool the wax, and then it's a skinny candle. You dip it again and it keeps building layers and layers until it has the thickness you want. Okay, that's one way to make it, as you make a dip candle. Another one is just pour it into a mold. Okay, so I melted this pot. I had all these candle shards, right? And you put them all in there. You pull out the dead wicks, and now I have liquid candle wax. And I left it on the stove too long. It ignited. You can't put water on it.
Oh no.
It is hotter than boiling water. So if you put water in there, the water will be heated, start to boil, and then it'll boil fragments of flaming wax out of the. So there's only one way to put out that fire.
Throw it out the window. Hope its potential energy is high enough.
Yeah, now you're going to give it extra potential energy, or kinetic energy. So no, you got to take a lid and cover it, and that'll smother it.
That's a less exciting answer.
It's totally less exciting, but I knew enough.
To suffocate it.
I knew enough about you're suffocating it. I knew enough about thermodynamics that's how you do that. So the candle doesn't all burn at once because it can only burn a little bit at a time, and it burns its way down. And there you have it.
Nice. Well, happy birthday, Lena. I
yes,
assume.
However old you are. Hey, StarTalk fans. I don't know if you know this, but the audio version of the podcast actually posts a week in advance of the video version. And you can get that in Spotify and Apple Podcast and most other podcast outlets that are out there. Multiple ways to ingest all that is cosmic on StarTalk. Oh, by the way, these are all our Patreon supporters. They pay.
Amazing.
So you get to ask questions as a Patreon supporter at our entry-level amount, which is like $5 a month. So go for it.
All right, so we have Alan Rayer. He wrote, "Hello, everyone." Waving emoji, cowboy emoji. It's Alan from Lithuania. A lot of cowboys there. Always wondered about gravitational waves. Please explain how and what did they actually detect in 2015?
Oh, very nice. Yeah, so that's the first detection of gravitational waves was then.
Nice.
Interestingly, it was the centennial, the near centennial. I think the prediction came out in 1916, but basically the centennial of Einstein's prediction that such a thing even exists. So it took a century to verify that what he predicted was correct. So just to put that in context. All right, so the way this works is, according to Einstein's general theory of relativity, you're here, and we say you have a gravitational force. I don't know if you knew that, but you do, right?
I like it.
Okay, and the more mass you have, the more is your gravitational force.
I've had an increasing amount of gravitational force over the last few years.
Is that right? Okay. So it'll go up according to your mass, and we can measure that, more importantly. If you move through space and time, then your gravitational field needs to respond to that in some way, because it used to be over here and now you're over there. Newton described gravity as just a force at a distance, okay? Action at a distance. But he was still mystified. How could it gap the vacuum of space? What's going on? How do we know each other? How do we know about what? Why do we know? Why? He knew his equations worked, so he went with it. But
that's some confidence.
It's still.
He's like, I know these are right. I can't prove it, but I'm 100% sure.
I can't demonstrate it. What's going on in the mystery of the vacuum of space? But it's working. So
Exhibit A, trust me.
Trust me. So it's working. And Einstein said, gravity is not so much action at a distance. Gravity is a is a disturbance in the fabric of space and time. So, disturbance is too violent. It is a shape of the fabric of space and time made by the existence of matter and energy wherever you might find it. Let's take a black hole, for example. A black hole is such a distortion of space and time that light cannot even escape. That's why we call it black. And you can't come out, it's a hole, black hole. Best named thing there ever was, ever. So if you're just somebody wandering by a black hole, you'll feel your trajectory altered by it. Newton would say that's action at a distance. Einstein would say that is the shape of curved space-time. And you're just following where space and time wants to bring you. It's like in NASCAR, are they actually turning left? No, because the track is banked. The bank turns them forth, turns the cars
I feel like the
forward.
drivers would be very upset by this. Like, what are we training for?
Yeah, so their steering is primarily maneuvering in the traffic rather than making a left turn as they go around the track. So the track is shaping their path. In the same way, space and time will shape the path of anything moving, but light is the best tracer of this. What happens when two black holes collide? OMG. Black holes collide, they are already a disturbance in the space-time continuum. Now they come together, it is such a disturbance that they will create a ripple in the fabric of space and time, emanating at the speed of light. A ripple, because as they come closer and closer, they spiral in faster and faster, and then they come together, and right at that instant, poof, there's a ripple. The first of these that was discovered have been traveling for 3 billion years. How do you detect it? We need special equipment. We call it LIGO, Laser Interferometer Gravitational Wave Observatory, sensibly abbreviated LIGO. So they have two, I forgot how long they are, kilometer-long tunnels, evacuated, no air. They have lasers that simultaneously go up the tunnel and back from a mirror that's at the other end. These two laser beams know about each other. They are coherent. They march to the beat of the same drummer when emitted. If on the up and back trip, something happened to the fabric of space-time, then one of those paths will be slightly different from the other, slightly longer or slightly shorter. And then the waves will no longer match up. And you can conclude that something happened here that didn't happen there. They're at right angles to each other. So this wave, this gravitational wave, as it washes over the observatory, depending on which angle was oriented relative to the wave, they will stretch or expand by different amounts from each other. And they measure this. They measured it. They knew what two colliding black holes should look like in their experiment, matched up. The announcement gets made, Nobel Prize is awarded. Now, just for context.
You said with a tone of voice that it was later discovered that it was wrong.
No. I have a follow-on to that.
2017, they took it back. Turns out one of them just jostled the machine a little bit.
No, they only discovered it in 2015. Nobel Prize is later.
Gotcha.
Okay, all right. So, many people don't know that Einstein wrote down the first equations that enabled the laser to be invented later on. This is crumbs on his plate.
Right.
Okay? When you're that brilliant, crumbs do great things because you're focusing on the main events, like the theory of relativity and other things.
The back page of his notebook just said tunnel laser.
So Einstein invents a new theory of the universe, the general theory of relativity, that predicts the existence of gravitational waves. Shortly after that, he writes down the equation that permits the invention of the laser. Decades later, people invent the laser. Decades after that, they use the laser to measure and discover the existence of gravitational waves.
And entertain cats.
Yes. Einstein's a badass.
100%.
People getting Nobel Prizes off of crumbs that fell off his plate. He should have had 8 Nobel Prizes.
Right. Did he get one?
Yeah, he got one. He got one.
Okay, good.
He got one. but for other stuff. I mean, not for his greatest work. He did for really important work, but not his greatest work. He demonstrated that atoms actually exist. Like, so that's pretty good.
That's, yeah, I would say. Yeah.
And he demonstrated that light comes in discrete packets called photons.
Which we just talked about.
We just talked about. So that's good.
That's pretty good.
If you do that in a lifetime, you did good. But he did that and then just kept going.
Yeah, but at the same time, I was learning magic and you were nearly burning your house down with the biggest wax candle.
That's the backstory. And the lead scientist on this was Kip Thorne.
Yeah.
Kip Thorne. People who read movie credits will recognize Kip Thorne as one of the co-executive producers of the film Interstellar.
Nice.
That's how you knew if there's going to be any black holes in it, they're going to get it right.
Yes.
Okay? You don't have to double check that one. He's got it. Yeah. Yeah.
I love that.
All right, give me some more.
All right, well, you were talking about the fabric of space, so it makes sense to bring this question up because Matt D wrote, "Greetings, Dr. Tyson. I'm Matt from Oklahoma and have a question about the fabric of space. In all caps, what is it? You tear it like cloth fiber and sew it back together? Take it easy, Matt."
Okay. All right. So he has issues with the word fabric.
Maybe. I mean, it sounds like he thinks it is a fabric.
Well, it does stretch, Lycra style, all right? So the universe stretches, but we don't know how much longer it will continue to stretch.
Oh, it's like my pants. Eventually, it snaps. Been there, done that.
I think we did a whole episode or a whole section of an episode on the future of the universe. One of the possible futures is it will expand so rapidly that the fabric of the universe cannot keep up with it, and it will rip. And it's called the Big Rip. And I'm terrified. I'm terrified by this because I finally grew accustomed to the stretching of space and time, whatever even that means, right? Now you're going to tell me it's stretching and it's going to rip? Oh my gosh. So
do we know where it's going to rip? Are we near the rip site? Do we need to move a little bit?
No, we put some pre-stitches in it to keep it going?
Yeah.
No, it would rip at its very core. All places within the fabric would just disassemble. Rip and fabric go together as two words. But before we use the word rip and the fabric, we spoke of space as a rubber sheet that stretches. And maybe it can stretch forever. Like, we don't know. We just don't know. So now the specifics of the question was what?
It just said, what is it?
What is the fabric? All we can say is space behaves as though it is a stretchy substance. Pick any word you want to give it.
Right.
Maybe we should have called it the Lycra of the universe.
Sure.
Or the
neoprene.
The neoprene. Right. I don't know. Call it anything, but we try to find an analogy that can make it more understandable to you, to anyone, to ourselves. So fabric of the universe seems to fit the bill very well, right on up to the rip.
Right.
So that's why. And
that's when everything in the universe disassembles, including us.
Oh, you're made of things in the universe. So yeah.
I was trying to be optimistic.
Yeah, all the electrons, protons, and neutrons, they're not all going to break apart, but you'll be intact. Okay,
yeah, exactly.
That'll be.
Do I feel it?
Yeah, I'm terrified by it. It is, if it happens at all, it'll happen in 22 billion years.
Oh, so we're okay. We're okay.
No, I got it on my calendar. So fabric is metaphor, but it's a very apt metaphor for what the universe is, because the universe can curve. It can curve back on itself. It can stretch. If you're not happy with fabric, come up with another term, but I think we're good.
That's pretty good.
All right.
All right. This question comes from Geezer Windbag. Greetings, Dr. Tyson. I'm curious why we say the universe exploded in the Big Bang. It seems to me more likely that the singularity expanded and fragmented, and the universe we see is still all within the singularity. An observer outside the original singularity would still see a singularity, though from our perspective, the universe is incredibly huge. Thoughts?
Okay. So a couple of things. If he doesn't like the word explosion, I'm okay with that, because the singularity that birthed the universe was the rapid stretching of space-time.
There we go.
Okay. See what I did there? So the rapid stretching, you can say, was there an explosion? You know what an explosion is? It is a rapidly moving shock wave within a medium. That's what blows out windows and blows down doors. It's a shock wave moving through the air. Well, the Big Bang is not a thing moving through something else. It is the expansion of space and time. So it's more accurate to say it's the big stretch rather than the Big Bang. The Big Bang was used pejoratively by, we're now going back 70 years, by an opponent of the Big Bang who couldn't imagine the universe would begin this way. He wanted the universe to be in a steady state at all times. And so he used the term Big Bang as an insult to the ideas that people were having.
He came in and he said, you know what, this theory is a big stretch. And they're like, you have no idea how right you are. That's exactly right.
This is a stretch. That's it. So yeah, it's metaphor, but we're good with it.
All right, cool. Well, thank you, Geezer Windbag.
No, but he asked something else about it.
Well, he said, is it more likely that the singularity expanded and fragmented and the universe we see is still all within the singularity?
We are no longer the singularity. So anyone observing us will not say they look like a singularity. The interesting question is, if you look at the math of our universe out to the horizon, the density of matter within it, the size of the horizon, if you run the math, we have all the same properties of an authentic black hole. And black holes have singularities in their center. So are we some mondo black hole? Is there a point where the similarities end? We don't know.
We could all be in a black hole?
Yes. I have a book on my shelf that describes the new space-time that opens up after you fall into a black hole. Time changes for you. It ticks more slowly relative to everybody outside the black hole. So as you fall in, you will see the entire future history of the universe unfold before your very eyes and a new space-time continuum open up.
That sounds awesome.
A whole
Minus the being ripped apart.
Minus the being ripped apart part. Yeah. So if the black hole's big enough, the tidal forces won't rip you apart. You can survive the fall.
Oh, that's cool.
Yeah, it's good.
It kind of feels like a way to go. Like if
I totally want to go that way. Don't, rather get hit by a bus or laid up in the hospital, launch me into a black hole. I'll give all my reports until I can't. Yeah.
All right, so we have Eliezer Vega. Hello, Dr. Tyson. This is Eliezer from Puerto Rico.
Puerto Rico.
I love that place.
Is that your best way you could pronounce it?
Puerto Rico.
All right. I'll give you a B plus.
All right.
Puerto Rico.
I have a last gap to fill with gravity. If gravity is the effect of the mass bending space, then why, when a star goes supernova, space still bent for a black hole to form instead of immediately unbending? It is as matter is blown apart, or better said, what makes space remember what was there before, so when it blows and matter is dispersed, space won't recover back, but stay bent as a black hole. Did you get all of that?
Wow. Stars above a certain mass, when they die, will go as supernova, and they'll leave behind a neutron star. Stars of even higher mass, we're not entirely certain of the boundary of this, but stars of a higher mass can go supernova and make a black hole. Stars of even higher mass, the supernova never gets out. Black hole all the way. So only in that last case is all the mass of the entire system part of the black hole. And the space-time curvature at the end was the same as it was in the beginning. Whereas the one where some gets blown out and others become a black hole, yeah, that black hole does not have the full gravity that the whole system had before because half of it got blown away. It's that simple. So he's right to think about this, but the answer is not that deep.
That's pretty good.
Okay.
Yeah.
Mm-hmm.
Matthew Jury wrote, hello, everyone. How can a gravitational singularity exist if infinite curvature means infinite time?
We do not have a good way to talk about the singularity.
Would you say the jury is out?
What I would say is that's why we have string theorists. To bridge the gap between quantum physics and general relativity, one, the theory of the small, the other, the theory of the large. But at the beginning of the universe, the large was small. Whole universes were operating in the quantum realm. And
I've seen Ant-Man. I get it.
Yeah. Well, there you go. Okay. So if that's the case, what's happening at the singularity? Because you don't get singularities in quantum physics, you get it in general relativity. So that's where it's been said the singularity is where God divides by zero. Have you divided by zero lately?
Error.
Yes.
Yes.
error.
I do a magic trick where I have people put stuff into a calculator, and if they divide by 0, there's no magic trick because there's just an error. So I very much, it's very salient for me.
Wow, okay.
To avoid the divide by 0.
If you divide by 0, it's an error. It's undefined. We don't know what to do there. Yet we know these two theories work in their own realm, their own regimes, the small and the large. You bring them together, it's a shotgun wedding that won't necessarily work as you had planned. So we got top people working on it. So no, we can't tell you what's happening inside the singularity.
All right.
Remains a mystery, yes. Have you ever wanted one of your questions on the universe answered? We all have questions about the universe. From black holes to quasars, quantum entanglement, wormholes. There is no end to the depths of cosmic curiosity. Well, the entry level of Patreon membership with StarTalk gets you just that. I think it starts at $5 a month. You have access to the question line that reaches our Cosmic Query programming. And not only that, we produce a special Cosmic Queries installment just for Patreon members.
So if you weren't the director of the Hayden Planetarium, what do you think you would be doing? What?
Okay, but this had to be another universe. It wouldn't happen in this universe.
Okay.
I'd be a songwriter for Broadway musicals.
Ooh!
So that's the entry level, and the perks ascend from there. There's a level, in fact, where we send you an autographed copy of one of my latest books. Right now, it's Starry Messenger, Cosmic Perspectives on Civilization. And it's signed with my fancy fountain pen with purple ink. So I invite you to just check the link below. And all of that money goes to our ability to experiment with new ways of bringing the universe down to Earth. So thank you for those who have already joined. And we welcome others to participate in this grand adventure of what it is to bring the universe down to Earth. As always, keep looking up.
Yogesh Jog wrote, "Hello to my personal astrophysicist. If someone keeps traveling back and forth at Planck length distance, does it mean that it's traveling eternally?" He did put a parenthetical which says, an idea/attempt to say that the particles don't come in and out of existence. They're just traveling eternally at Planck length distances, and 4 forces hits them at the right time to let them exist in this universe.
Okay. Yeah, I don't know what he's talking about. I can tell you this, a Planck length is the smallest unit of length that we can measure. It's very, very small. It almost doesn't make sense.
It's not the size, it's what you do with it.
It turns out in quantum physics, everything is in motion. Everything vibrates at all times. So
exhausting.
To say you have something moving back and forth across a Planck length, all matter is doing that at all times because everything is always in motion. Always. So to say, let's do it at a Planck length and it's time at infinity, I don't know how the connecting Planck length and infinity time in that question, but everything is always in motion at all times. And it has nothing to do with measuring time at infinity.
Gotcha.
All right.
Especially in this city, huh? New York City. All right, I'm fired. Okay. This is from Vinay Kashyap. He says,
What's
hello.
the first name?
Vinay?
Vinay, okay.
Vinay?
Mm-hmm.
It's how I would say Vinny if I was being fancy.
Okay. Vinay, yes.
Vinay. Hello, this is Vinay from India. I was just wondering why black holes can't just be dark matter. There seems to be a lot of them. They are massive and seem to have more gravity. Most importantly, we can't see them.
Let's list the dark matter candidates. Would there be dark clouds? Could there be vagabond planets that are not illuminated by a host star that got ejected into the galaxy? Could it be black holes? It turns out the physics of the early universe limits how much ordinary matter there can be. Black holes count as ordinary matter because you make them from ordinary matter. It limits it. There's a delicate set of knobs that we're turning in the early universe to understand what the universe was and what it became. And so these knobs are they're fascinating because some combinations of knobs don't work at all. You don't get a universe, or you get a universe that's very different from what we have. So the problem with dark matter is it doesn't interact with ordinary matter in any way other than by gravity. And so if you look at what it does in the universe during the early universe, it can't be regular matter. Otherwise, we'd have a universe completely different from what we have. And black holes are made of ordinary matter. It has to be something completely exotic beyond the measurements we've made of electrons, protons, neutrons, atoms, molecules, solids, biology, chemistry, physics, psychology. Everything that we know and love falls outside of what dark matter can be. So let's say we have very good theoretical evidence, theoretical support for why dark matter can't be black holes.
All right, we have Mike Mohammed Kake. I assume it's pronounced as a bird would. Kake. Greetings, Dr. Tyson. Mike Kake from Berlin, Germany. While it's well known that most of Earth's energy originates from the sun, I'm curious about the source of tidal energy. Can it be traced back to the sun, or does it stem from a different origin? Is it possible that tidal energy has multiple sources?
I love that, because when we talk about green energy, we're talking about renewable energy. And if you could turn plants into gasoline, which we do with ethanol, which is the one from corn.
My wife is from Nebraska, so she's going to be very disappointed if I don't know the corn thing.
Kick your ass. Yeah, I think ethanol, we get that from corn.
Yes.
And corn is a renewable resource. All right. It's not fossil fuels where you take it out, you can't wait for new fossils to form.
Right.
All right. That's not how that works. So that's why one is renewable and one isn't. By the way, do you know the original energy source of fossil fuels? The sun.
Oh, there you go.
Oh, you're going to say dinosaurs?
I was going to say dinosaurs.
No, it's mostly plant life at the time. But where does plant get its energy?
From the sun.
The sun.
Photosynthesis.
So all fossil fuels is energy from sunlight. It's just not renewable because it's a one-time use. So all plants get their energy, all surface plants get their energy from the sun. You eat plants, you get energy from that. If you eat meat, you eat some animal that ate an animal or ate plants. And so the tracking is back to the sun. Now here's something deep. What generally do fish eat?
I was going to say fish food. That was what came to mind first.
Fish food, of course.
They eat, well, do they eat stuff in the ocean? Algae and stuff?
Eat other fish.
Yeah, but then who?
Well, I'm getting there. Good one. Good one.
Wait a second.
This is where I'm headed. Okay.
This is turtles all the way down.
That's all the way down. But it can't go all the way down. This is why you can't. There's no such thing as a stable cannibal society. It's not stable.
Amongst other reasons, probably. I'm sure there's like
I'm sorry. Yeah, I'm not ranking the reasons. I'm just offering reasons. Because you can't just keep eating each other.
Right.
Because you will run out of people.
Sure.
But you can say, well, why don't we reproduce faster than we eat? That's not possible, because if you're a fully nourished human being, you have to eat at least a whole other human being.
Right.
Because you are a human being, right? You have to eat at least that. And if you just run the numbers, you can never have a stable thing where you're only eating other things that are being born within it. At some point, you need a source from the outside. So the big fish eats the littler fish, eats the littler fish, eats the littler fish. This goes all the way down until you get to plankton. So the fish start eating all the way down.
Right.
And then you get to some point where if that's all that was happening, the ocean would just eat itself and there'd be no living things, no fishes left in the ocean. Something has to come in from the outside. Somebody's got to deliver the groceries.
SpongeBob. He has a pineapple under the sea.
You got it. You got it. His pineapple is actually in the sea.
Yeah, that's true.
Okay,
we need to correct that.
Okay, I'm just saying. I don't mean to get all technical on SpongeBob, but you finally reach the level of plankton.
SpongeBob.
So,
Nailed it.
And there are two categories of plankton, okay? One of them eats other life forms in the ocean. The other, for nourishment. The other gets its energy from the sun. and they all live right at the surface where they can get sunlight. That is the base of the food chain of the ocean, the phytoplankton. If you kill them off, you will systematically render extinct every other fish in the ocean that eats other fish. Now, there might be some fish that eat like the kelp and seaweed and things. There might be some, but where does kelp get its energy from? The sun.
Right.
Okay, so the sun is the ultimate source of all energy in the typical fishes that we think of in the ocean. However, the ocean in certain parts is open to what's below it. What's below the ocean? Well, you get through the crust, and below the crust is the mantle, and in the mantle is magma.
Beneath that Godzilla, according to the films.
Oh, is that right? Okay, I did not know that.
The Hollow Earth.
Yes. Thank you for enriching this scientific discussion here. So I keep thinking this should be Magma PI. That would be a fun sort of.
A really cool mustache that is past the point of boiling.
So below the crust, we get the mantle, and within the mantle is magma, okay, molten rock. Earth has retained still a considerable amount of heat from when it formed, and that heat wants to get out, and it gets out through volcanoes, through crevasses in the bottom of the ocean. The mid-ocean ridge are just such a place. One of these ridges goes through Iceland, the country. Iceland is growing because the continental plates are separating, magma gurgles up, hardens, and is more Iceland. Okay?
That's a very good plan for the future.
We have discovered life forms that thrive on geochemical energy enabled by these hot vents at the bottom of the ocean. In apocalyptic Earth, even if the sun burns out, if someone plucked the sun out of the solar system and we fly off at a tangent into interstellar space, we will all die rapidly. But the life forms at the bottom of the ocean that are warm from the magma oozing up through the vents, they'll be just fine. They will survive the death of Earth's surface. So that's another source of energy. By the way, geothermal energy, because Iceland is sitting at the separation of two continental plates, they're almost entirely geothermally driven. Their carbon footprint is minuscule. They have so much energy, they send water under their streets so that it never gets icy in the winter. We don't need snowplows, just heat the streets.
Right.
So that's another source of, it's renewable in the sense that it's like a near infinite supply of Earth energy available to us, all right? Yes, it would one day run out, but not really because we had something to do with it, all right? It's the volcanoes got, have you seen Earth get angry? All right, it's got a lot to kill us in the future. So that's another source of energy. So these are different ways. So another way is hydroelectric, okay? So there would be dams. You have water up here, and that has a certain height that it can fall, gaining kinetic energy.
Sure.
And it comes through a turbine that then drives a generator that makes electricity. So what's that based on? How did the water get up to the top of the dam? The sun evaporated it from the ocean, brought it up to a cloud. The cloud moved over the land, rained on the land. It brought the water up to the upper levels. That's solar power. Hydroelectric is solar power. How about wind? Why does air move horizontally on the Earth? You know what Ogden Nash said? He said, wind is caused by trees waving their branches. And I thought that was good. Like, how would you know it wasn't that?
I feel like we do know, though. I feel like we're about to lead into the fact that can't be.
Yeah, it was just it's a clever, kind of fun, stupid observation.
Yeah. The only thing I know about Nash is he has great equilibrium.
Oh, that's the mathematician.
Different Nash.
That's a totally different Nash.
And then the founder of Nashville.
Oh, I don't know who that would be. Yeah.
I assume he's a Nash.
So wind comes from the unequal heating of Earth's surface that creates air that rises, air that falls, and that also creates pressure differences that'll move air horizontally as well as up and down. So wind energy is solar energy. Set up a solar panel. What do we call that energy?
Solar.
Solar.
Yeah. Yeah.
That's taking out the middleman, and now you have solar power is solar energy. So all of these are solar power that is in principle renewable until the sun runs out of energy. All right. How about tides? Tides slosh back and forth. Love it. Well, we commonly associate tides with the moon.
Sure.
So the moon tides have nothing to do with the sun. So if you have a tidal thing that drifts with it and generates energy, it's also renewable because you're always going to have tides, but it's not traceable to the sun. However, 1/3 of the tides you measure comes from the sun.
How's it doing that?
Well, the full name is lunisolar tides. Loony moon, solar sun, lunisolar tides. The tides we all experience are lunisolar tides. And the moon is like 2/3 of it, and the sun is 1/3 at all times. At all times. If you're using tides, some of that is the sun. Most of it is the moon. And so there you have it. That's the difference from all of this. But if you pull fossils out of the ground, you're not renewing that. And when you run out of fossils, you're done. Oh, by the way, there's thermonuclear fusion. We haven't harnessed it yet. We know how to create it. They're called bombs. But when you harness it,
that's a lot of energy.
That's a lot of energy. You can create a power plant, and that's fusing hydrogen together to make helium. The sun does that every day. So we just be mimicking the sun on Earth. It's the nuclear fission that has dirty byproducts. And that's what the original atom bombs were made of, fission bombs. But nuclear fusion, that's the holy grail. But I saw a bumper sticker once that said no nukes. So it was a very green, sort of progressive, left-leaning bumper sticker, no nukes. But the O in the no was a sun.
Which is the ultimate nuclear weapon.
The ultimate nuclear furnace is the sun. Okay, if you had no nukes, you wouldn't be here. All right, well, you know what they mean, of course. They don't want like nuclear energy. They want solar energy, but solar energy is nuclear. I think at the time I saw this bumper sticker, it was still in the Cold War. So maybe they were talking about the nuclear arsenals for sure. But the fact that they had a sun there, it still tells me that they were thinking of generating power.
Sure.
Yeah, use solar power rather than nuclear power. But one other quick source of energy, because the big problem with solar energy is how do you store it? If you want to use it at night, how do you use solar energy at night? You can't. Okay, tides still move in and out at night. That works. Hydroelectric, you can use that at night. That all still works. But how do you use solar panels? So there's talk now of using solar panels to lift heavy weights up a hillside, to turn photons into potential energy that then becomes kinetic later. So that's your storage battery becomes solar power lifting all these weights up into the air. So it's a successful way to store the solar energy that you had earlier, and then you could draw from it at any time of day or night.
That's amazing.
It's very clever. Yeah.
There's a lot of balls at the top of hills and like, don't touch them. This is
we
powering the whole city.
Yeah. So anyhow, there you have it. That's everything that was not even asked in that question answered about where energy comes from.
And I like dirty byproducts. I'm going to make that my next comedy album.
Oh.
It's going to be called Dirty Byproducts.
Dirty byproducts.
All right, we have one more question.
We'll get time for one more. Go, give it to me.
This is from Cicero Artifon. Hey, smart
That's a cool
people.
name. You got to admit that's a cool
really
name.
cool name. That's like a sci-fi hero
I
name.
want that name, Cicero
Yeah,
Artifon.
he's the hero of like a Blade Runner kind of trilogy, Cicero Artifon.
Yeah.
Or he's like the president in the Hunger Games.
You need an evil variant of this.
Yeah, exactly.
Yeah.
He can go either way. So hopefully this Cicero is leading towards good.
Yeah.
But he said, hey, smart people. Cicero from Toronto, Canada. He's from Canada, so probably good people.
Mm-hmm.
Neil mentioned once that the element osmium, 76, is heavier than gold, 79. How can that be possible? Don't the elements have an increase of mass the lower they are on the table?
He's slightly misremembering what I said.
Oh, no.
Okay. That's okay. So as you go up the periodic table, the elements become more and more massive.
Right.
More and more massive. No doubt about it. You're packing more protons into the nucleus. He mentioned how many protons were in osmium. I forgot he said 76. I'll believe him. Gold was 79, was it? Okay.
That's what he said, yeah.
Okay, uranium is 92. These are bigger, heavier atoms all the way. That's not what distinguishes osmium. if you create a lump of these materials, a lump of osmium, a lump of gold, a lump of them, how close together will the atoms pack in this lump that you have created? That's the question. It turns out, given the properties of atoms and the periodic table and the quantum physics of nuclei and energy levels in atoms, you can pack osmium atoms closer together than all the other kinds of atoms, thereby making the densest element, not the heaviest element, the densest element, because now they're packed in close together. So osmium would make the world's best paperweight.
I mean, it could make a wedding ring. How come we don't use it in place of any of these precious metals?
Why'd you want it to be heavier? We like gold.
This way you remember that you're married. I'd be like, oh my God, I can never forget.
No, then it's the
I can
ball,
barely lift my hand.
Then it's a ball and chain analogy. Here's the osmium ball you're going to carry around. So that's the only difference. And just to quantify how dense these things are, a cubic foot of gold. Oh my gosh, it's like
right.
Gold has 2.5 times the density of iron. That's gold. And osmium tops that. And osmium, I think, may be used in the tips of some fountain pens because it has to be very hard because you're pressing on it. There's a lot of pressure there. So it has its utilities.
Sure.
But paperweights are not among them.
Right.
So that's why. We're talking about the density of an aggregate of those atoms, not the weight of an atom itself.
Nice.
Yeah.
Well, thank you, Cicero.
I think that's all the time we have.
Amazing.
Well, it's great to have you back.
Thank you. It's been so great to be here.
It's very good.
I really appreciate it.
Yeah. And you're, so how do we find you in the city?
They can find me on social media at Harrison Comedy on Instagram.
Oh, Harrison Comedy?
Harrison Comedy.
Good,
And harrisongreenbaum.com is my website.
Okay, excellent.
Yeah.
And you perform?
I perform every night. I'm all over. I have my off-Broadway comedy and magic show on Saturdays at
Call
Asylum
me
NYC.
when you're on Broadway. I don't need this. No, that's great. So,
Well, if enough people buy tickets, maybe.
so it's a gig. No, it's great because you do magic and comedy.
Yes.
And we love you here. We'll try to get you back.
I would love that.
All
Thank
right.
you so much.
All right, this has been StarTalk, Cosmic Queries Grab Bag Edition with Harrison Greenbaum.
That's me.
All right. We'll see you next time. As always, keep looking up.